Hi, this is Professor Jiamei Chen at California State University, Long Beach. In this video lesson today, we'll look at how to graph functions via plotting. Define the graph of a function as the following. Graph of a function f is a set of ordered pair x, f of x plotted in the coordinate plane where the point x is chosen in the domain of f. I'll explain a couple of concepts here. First of all, what do we mean by ordered pair? An ordered pair of points is so that the order at which we write the point is always the same. So in this case, we write the x-coordinate first and its corresponding y-coordinate second. We have to keep that order all the time, every time we write down a point. The second concept here is the coordinate plane. The coordinate plane is defined uniquely based on what we have as a point. In this case, here we have the coordinate plane defined by the variable x and the f of x, like that. The last concept here is that we have to make sure we can only use points from the domain of the function. Beginning of the time, as we're just learning the graphs of functions, we typically get graphs by plotting points. And as we have done enough of them, we want to use these prior knowledge that we've built to speed up the graphing process. Let's look at a few examples next. We start with something that is a very basic. We typically think of f of x value as the output value, which is called the y variable. We start by constructing a table of values that we're going to use to plot. Typically, we wanted to select a balanced set of points that includes some negative numbers, some positive numbers, and maybe 0, because 0 is typically the easiest point to graph. Potentially, you want to include some fractional values in between. I'm going to lay down our table of values here. I'll start with the independent variable here, x, and the f of x, its corresponding output, or the function value. Let's do first. If x is equal to 0, and squaring that certainly would still make it 0. Let's pick a negative 1 and positive 1 to do next. If you take the value 1 and square that, you will still get 1. If you take negative 1 and square that, you will get positive 1 back. Let's do a couple more, say 2 and negative 2. If you square the number 2, you should get 4. You square the number negative 2, you should get 4 as well. Remember, squaring any real number always returns a positive result. Maybe enough points at this point to help you graph. It may not be. We'll just have to see. Let's try. First, we lay down the coordinate system. Remember, this is going to be x-axis, and it's going to be the y-axis, which is given by the f of x value. We start with the point 0, 0. That's this point right here. This tells you that I have the point 0, 0 on the coordinate plane. So I'm going to first lay down that point. The second point here will be 1, 1, x value 1, and y value 1. So I'm going to go down here, label my 1 unit for the x, and then go up 1 unit for the y, and that's where the second point is, at 1, 1. I have another point that's 2, 4. I go down to my x-axis and find my point 2, go up 4 units, 1, 2, 3, 4, to find its corresponding y value on that direction, and go the other way. If I have the point negative 1, 1, it would then go to here, negative 1 direction, and then go up 1 unit in the y direction to label my point here. This last point is negative 2, 4. That means on the x-axis I start with negative 2 and I go up 4 units to find my corresponding y value. I think the hardest part about graphing is now you've got these points laid down on the coordinate system. How do you actually connect them? Do you use a straight line or some sort of a curve? If you do use a curve, should it curve up, curve down? How do you do it? You want it to develop some sort of how the points are connected by looking at how far apart points are. For example, if you look at the positive direction, each x value is 1 unit apart. But if you look at the y direction, between the point 1 and the point 4, so this is the point 1, this is the point 4, they're actually 3 units apart. So here you have 1 unit apart, but then 3 units apart on the y direction, so it's growing a lot steeper from point 1 to point 2 when you compare it to the growth from the point 0 to point 1. So it can be a straight line, because a straight line basically is a constant growth rate all the time. So certainly we're going to have a curve to connect the points between 0, 1, and 2. This is how it's going to grow. It's going to curve up. Occasionally, your curve might be a little bit off, and you can kind of cheat a little bit by thickening that dot to make sure it sits on the curve. On the other hand, you have the negative direction, which grows exactly the same way, and it's just going to be kind of a mirror image of the right-hand side. You think the graph actually stops there, where you stopped graphing? Typically, no. We only stop there because that's the number of points we got. I typically put arrows on ends to indicate the same behavior continues on. Like I said, as you start to graph more functions, you want to build a library of these prior knowledge. Next time when I ask you to graph the x squared function, you should immediately think, well, that's the parabola graph, and it should look something like this. But with the minor modifications given, sometimes we have a negative in front of x squared, sometimes we have a constant attached to the x squared, and sometimes we actually have a constant connected to the function with the plus or minus sign. All these things actually modified the shape of the parabola and also the position in which the parabola sits on the coordinate plane, but the general shape, opening up like this or either opening down, it's not going to change. It's still going to be a parabola graph when you see the function x squared. Next, let's graph g of x equals x cubed. Try to do this yourself. Pause the video if you can, and then try to figure out the table of values to plot and then try to graph it yourself. I'm going to try to use the same set of points here to illustrate. Start with the point 0. If I 0 cubed, I would still get 0. Take -1 and then cube that. Be careful, when you're cubing a negative number, it will come out to be a negative number as well. So it's going to be -1, and if you do +1, cube that, well, that's still going to be a +1. Similarly, when I take -2 and cube that, that's multiplying -2 3 times. So that's -2 times -2, that's +4, and then +4 times another -2 gives you a -8. +2 here and cube that, that should be a +8. And notice one thing that is different from the calculation before, when we did the x squared. When you square a number, either positive or negative, it always comes out to be positive. But here, when you're cubing it, you actually get opposite signs. So here you get negative number, and here you get positive number. So your y value is not going to be exactly the same anymore. Notice that the shape of the parabola from before, it was a mirror image between the positive side and the negative side along the y-axis. Here, we do not expect to see something similar. Here we start with the same coordinate system, x versus y. The y value here is given by g of x. The first point, 0, 0, is the easiest one to graph. You might want to label your origin, that's 0. You also wanted to start putting down tick marks. And let's do the next point, 1, comma, it's 1 first. So this point here is 1, comma, 1. So that's 1 point here, and then 1 point up there, and then that gives me this 1.1. Let's do the next point, 2, comma, 8. Point 2. Sometimes it might be that the y value is too big, it makes a tick mark too hard, so you can kind of cheat a little bit, because a lot of times we just ask you to sketch the graph instead of actually graphing a graph in details. So we just needed to get a sense of where that number a would be. So I'm just going to say that's about 8, and I don't need to label all the tick marks in between, as long as my scale is fairly accurate. So if I start with 2 in the x direction and just go up a units to hit my y, and I should land at that point there. On the kind of a negative direction of the x-axis, I have similar points. I have -1, but this time the y value is at -1 as well. And for x equals -2, my y value is at -a. So this is when you have to extend your axis a little bit longer. So it actually makes sense. Just say that's about -a right there. And I'm going to go down to hit my point at -a here. We can do a similar analysis as before to try to figure out how to connect the points. The rate at which we grow from 0 to 1 is certainly slower than the rate at which we grow from the point 1 to 2 on the x directions. So this definitely would be a curve as well. So I'm going to curve like this, and on the other hand, I have a curve going down like that. And supposedly, if you keep going, start doing points for 3, 4, and 5, you would expect that the y value grows a lot faster than that. Because just imagine if you take x equals 3 and then cube that, right away you get 27. So that's a lot bigger than 8, right? We think it's going to have this sort of a behavior, and it's just going to grow more rapidly like that. Now you should put the x cubed function in your library of the function graphs that you are familiar with. And next time if I ask you to graph or sketch x cubed, it should look like that, or something like that. Now, again, modifications, if you were to add a number in front, for example, a 2 here or a 1/2 there, it would only modify kind of how stretchy or how narrow the function looks. If I put a negative sign in front, it actually will flip your graph upside down. It becomes a mirror image of this one. If I actually add a number next to it, it will actually translate this graph along the horizontal axis. So all these things will modify the shape a little bit, but it's kind of a bigger picture, like just a generic shape still looks like that. Next, let's look at a very well-known shape as well, square root of x. One thing we haven't talked about yet in the previous examples was the domain, because in the previous two examples, it was pretty obvious that the domain for the functions are all real numbers, because there's no x values that we couldn't pick to evaluate the function. But in this case, let's actually think about what the domain would be. Is there any x values that you couldn't pick to make sense out of this? You can only use x values that are greater than or equal to 0. So the domain for the function is a set of all x such that x is greater than or equal to 0. Which means that when you're constructing your table of values, you can only use values that are greater than or equal to 0. Let's start from 0. And if you take square root of 0, you should still get 0. If you take x equals 1, square root of that, it would still be 1. Take 2, well, square root of 2, you actually have to maybe ask your calculator friend to figure out what that number is, about 1.414. You can do square root of 3, and that's about 1.78 something. Too lazy to figure that out. I'm going to use nice numbers because I know these are perfect squares, so when I take square root, it just comes out to be a nice number. So if you take 4, square root of 4 is square root of 2 squared, and that's what I mean by perfect squares. This number that you can actually write it as something squared. So the square and the square root, kind of their opposite actions, they cancel out. I would just get 2, and I can pick, if I really want to be lazy, I can pick 9 because I know that's another perfect square here. So that's square root of 3 squared, which again, square root and square cancels, leaves me with 3. Now I'm ready to graph down my x-axis and my y-axis. Notice that I put my y-axis very to the left of the x-axis because I know I cannot use negative values for my x. Alright, so here's my 0, and I start from the point 0, 0. 1, 1 is my second point. I have 2, 1.414, and I have 4, which is about right here. And that gives me the value of 2, and the next one will be 9, way out here, and that's going to give me 3, right about there. So this thing actually, it's got a slower growth rate than the previous two examples before. Actually flatten out a little bit as you grow on the x-axis. So when we connect the points, it curves like that. I want you to add this square root function to your library of your known functions. Next time when I ask you to graph square root function, you should look like this. It's very important that we start to develop a sense of graph correspondence to these well-known functions. If I ask you to sketch, for example, y equals 2x cubed, you should immediately think it should look something like, the x cubed function first, and then the 2 basically just modifies how stretchy or how narrow it's going to look.